Good morning and welcome to Blackhat. This is the second talk of the day. This is the reverse engineering track, and we have Charlie Miller and Noah Johnson here to talk to you about a new project they're working on.
Thanks. So I'm Charlie. This is Noah. Thanks for coming, everybody, and everyone at home. Hi. So today we're going to talk about crash analysis with BitBlaze. Okay, so what are we going to be talking about today? So first, we're going to go back to why is this talk important? So why do I care? And it has to do with fuzzing and the fact that people are starting to realize the hard part about fuzzing isn't actually finding bugs, but actually knowing what to do with all the crashes you find. And then we're going to talk about BitBlaze itself and what it does and how you can use it to help solve this problem. And then we'll move on to a bunch of real-life case studies. So first, I'll look at Adobe Reader and look at how, in general, these techniques can be used with crashes from there. And then we'll look at 4 actual bugs that were found with fuzzing and how you would use that use BitBlaze to analyze those crashes and figure out if they're exploitable, how what the underlying bug is, and that sort of thing. And then finally, we'll try to wrap things up. Okay, so how did I get involved in this? And I should point out, so you probably know me. I work in industry and I'm a consultant and all that stuff. Noah and the rest of the BitBlaze team are actually at Berkeley, so it's sort of an academic and industrial collaboration. So it's sort of, you don't see that too much. And so the question is how'd that get started? So about this time last year, and a lot of researchers go through this. After Blackhat, you've given your talk, and then you're like, okay, now what am I going to do? Right, so I started thinking about well, what kind of research do I want to do? This is like last August, and I typically my sort of interests are about finding bugs and that sort of thing, and I'm always kind of thinking about Pwn, next March. So I was like, well, what's some things I can use to find bugs that is something I haven't done before, and so basically the only guy I know from academia is David Molnar, who now works at Microsoft Research, but at the time I thought was still in academia somewhere. Anyway, so I called him up and I was like, okay, David, I need you to hook me up with someone who's writing tools in academia that find bugs, and these tools have to work on real binaries. You can't have any sort of restrictions like they have to be small or they have to be written in Lisp or whatever crazy things academics come up with these days. And then it has to work on real binaries. And I don't have source code. I don't have symbols. I don't have anything like that. And I want to be able to find bugs in these real programs. And so he's like, well, it's kind of tough. He gave me the names of a couple people, one of which was Dawn Song at Berkeley, who's here today. So I started talking to her about hey, I want a program that finds bugs, and she told me that, well, they kind of have something that does that, but she explained what BitBlaze was, and I realized that really it solves a different problem than I wanted to solve. So it's not about finding bugs, it's about analyzing crashes. So they actually have something that would be really good at that, and so I was like, well, that would be interesting, let's do that. So that's how I got interested in this, and let's move on to more discussion about why this is a problem and what the problem is. So until maybe a year ago, this wasn't a problem for me because the way that I looked for bugs was I would turn on my fuzzer, it would run for a while, and eventually it would find a bug, and I would turn it off, and I would exploit that bug and give a talk or whatever, right? So I didn't really have a problem with finding too many bugs because I only wanted to find one. But this year, in preparation for Cancer Quest, I wanted to find lots of bugs. And then I saw this problem. And the first person that I know who really talked about this problem was Ben Nagy, who gave a talk about an hour ago. So he's really the king of large-scale fuzzing out in the research world. I'm sure Microsoft does it as well, of course. So in 2009 at Syscan, I met him, and he was giving a talk about some fuzzing he did on Microsoft Word. So, .doc files. And so here's some statistics. So he found 200,000 crashes, and they were sorted into 61 bins, so 61 somewhat unique crashes. And basically, it was him and maybe a couple guys, and that was just too many crashes to analyze by hand. He couldn't do it. So it turned out of those 61, 4 of them were serious security vulnerabilities, and the rest weren't. And the problem was trying to figure out which of these were exploitable, and of the 4, like what was the actual bug. And so just to show that like he couldn't do this himself, he had to actually give these to Microsoft. And I know Ben, and that must have really hurt him to have to do that. So he gave it to Microsoft, and they helped triage them. And the point is, it was too much resources needed to analyze all the crashes. Okay. So then I had this problem as well. So I gave this talk at CanSec West, and in some ways this talk is sort of the continuation of that talk. So at that talk I talked about all the fuzzing runs I did, and I found a ton of bugs, and there were way too many. I couldn't analyze them all. So for example, in preview I found 1,300 different crashes, of which Crash Wrangler says there's really 220 unique ones, of which 60 are exploitable. So there's just no way that I can look at 60 bugs and 60 crashes and try to figure out what the bugs are and if they're really exploitable. This is too much for me to do. Likewise, in Adobe Reader, there were 30 to 40 crashes that I found, and 70 in OpenOffice. So it's like, this is a serious problem. And there's actually a lot of talks at Blackhat this year talking about that. So, I'm not the only researcher who's noticed this. Right, so more just about this. So the hard part now, I think, which is sort of sad, right? It should be hard to find bugs, but it actually isn't. So the hard part isn't finding the bug. It's sort of prioritizing which of the crashes to look at, figuring out which of the ones are exploitable. For the ones that are exploitable, figuring out what the underlying bug is, so you can either fix it or exploit it, depending on who you are. And then the other thing is, while fuzzing, eventually you can get it so automated that you can just turn it on, walk out of the room, and come back in a month, and there's a bunch of crashes. Trying to figure out how to, what the underlying bugs is. You can't really automate that. You can just make it easier. And so that's sort of the point of this talk is tools to reduce the time from crash to knowing what the bug is, or even further, writing the exploit. All right. So now I'm gonna pass it on to Noah to tell you guys about BitBlaze.
Okay, so I'm Noah. I work with Professor Don Song at Berkeley, and of course I've been collaborating with Charlie over the last few months. So BitBlaze is this binary analysis infrastructure that allows us to effectively analyze binary code. So in this talk, I'll give sort of a high-level overview of the 2 main research focuses of the BitBlaze project. The first is to be able to build a sort of a unified framework that allows us to very effectively analyze binary code and sort of addresses the common needs of security applications while also being easily extendable. And then once we have this platform, the second research focus is to be able to use the platform to enable a wide variety of new security applications. So this picture sort of visualizes what I just talked about. We want a unified platform that we can use to solve a whole bunch of different types of problems, right? So let's look at why this is hard first. Of course, in security applications, we can't avoid having to deal directly with binary code. Oftentimes we want to analyze commercial software that we don't have the source code for, or malicious code, and attackers don't usually release the source code along with their attack, right? So we need to deal directly with binary code, and unfortunately binary code can be very hard to deal with sometimes, as everyone here probably already knows, right? So first of all, binary code is extremely complex, and our analysis system needs to be able to model this complexity accurately if we want the analysis to be correct. So the size of and complexity of modern architecture instruction sets make this modeling very challenging. Another challenge is that binary, of course, is different from source code in that it lacks higher level semantic information. So as a specific example, the function abstraction doesn't really exist at all at the binary level. I mean, we can have call instructions, but I could call any arbitrary address, right? That doesn't tell me anything about where function boundaries are. And so we need to be able to deal with this. Also, lots of times we want to be able to analyze operations within the kernel and interactions between multiple processes. So this requires a whole system view, which poses greater challenges than in just traditional single program analysis. And finally, we need to remember we're trying to analyze malicious code sometimes, and code doesn't always want to be analyzed. So malware commonly employs anti-analysis techniques like code packing, encryption, or self-modifying or dynamically generated code. So based on these challenges, we have a couple sort of high-level design goals which motivate the architecture of the BitBlaze platform. The first is that we want the platform to be able to accurately model the behavior of programs. Okay? So we build precise formal models and then allow tools to sort of accurately reason about the program execution behavior symbolically. We also want to build a core set of utilities that sort of address the common needs of security problems, but can be reused or maybe target different architectures and easily extended. And finally, of course, both static and dynamic analysis have their own strengths and weaknesses. So static analysis is more complete in that we can explore multiple paths, but it's limited by things like indirection and pointer aliasing and a general lack of higher level abstractions. So dynamic analysis is not limited in these same ways, but we can only analyze a single path at a time. So ideally, we'd like to be able to combine both static and dynamic analysis to sort of leverage the relative strengths of both wherever possible. So before I talk about the actual implementation of our system, I want to sort of whet your appetite with some of the cool applications that BitBlaze has enabled. And there's a whole bunch, and I don't have time to talk about all these, but you can refer to the white paper or the website for more information. But the first one I want to talk about is vulnerability detection and analysis. So this is the most recent work, and of course, the bad guys are constantly looking for bugs in benign programs, right? But what about trying to find bugs in malicious code, right? So we're sort of turning the tables, right, and forcing the bad guys to have to write secure code. So using a modified version of our symbolic execution tool, we can sort of explore the execution space of a malware sample in ways we couldn't do before, because typically malware employs things like checksums and decryption routines, which are sort of hard to reason about. So once we've done this sort of symbolic execution and we have these constraints, we split them up and solve just a little piece of them and then use that to rebuild an input that exploits the program. So we've actually found vulnerabilities in 6 different classes of malware samples which could conceivably be exploited by an attacker over the network. So for example, you could take over a botnet or disable a Trojan horse. Of course, this raises ethical considerations which we won't get into here. But the next thing I want to talk about is model extraction. So we have a static analysis component which allows us to extract models of programs. So suppose we fed this tool a web browser, right, Internet Explorer, and then we extract a model for the function that determines the content type of any given object, right? Once we have this, then we can directly construct an input that causes the web browser to incorrectly infer the type for. And of course, this enables content sniffing cross-site scripting attacks, and we showed that Internet Explorer 7 is vulnerable to such an attack. Another application is protocol reverse engineering. So in security applications, oftentimes we want to understand network protocols or file formats. And traditionally, this is a manual process and is very time consuming, right? But we have this dynamic analysis component of BitBlaze, which allows us to analyze program behavior. So if we give this tool a program that implements a given protocol, then we can watch exactly how it processes messages in that protocol. And how it processes and parses these messages and constructs its own messages gives us a wealth of information about the structure of the messages as well as the semantics. So using that, we can then semi-automatically rebuild the protocol without access to the source code. So hopefully this sort of lets you realize how powerful this approach is. So next I want to talk about how we actually enable these kinds of applications. So BitBlaze is split up into 3 core components. The first component is a static analysis component called Vine, and Vine lets us do static analysis and symbolic execution, and it also provides a set of sort of core utilities for common types of analysis. The dynamic analysis component lets us run a program in an emulated environment and perform very fine-grained binary instrumentation and also extract semantic information from the operating system as well as the program and perform dynamic taint analysis. And finally, we have a symbolic execution components. Currently there are 3 of them: rudder, bitfuzz, and fuzzball. And these components use the functionalities which are provided by Vine and Temu to enable symbolic exploration. So for a given program execution path, these tools can generate